Okay, let's start. So this is week 3. So you can submit your quiz solution by PDF file. If you can convert your writings in iPad or Galaxy Tab to PDF file, you can upload that into LMS. So either way, as long as you upload your file as PDF file, it's okay. You can either write on your paper or you can write on your pad. I will announce about the quiz and homework after this lecture. Okay, so this week we are going to talk about integral. So last week we talked about the differentiation of single variable function, and this is the integral of single variable function. So concepts, I think you learned about integral as a inverse process of differentiation, because if you take an integration and then differentiation, you get the same function. So however, the definition is very different from the differentiation. So in the integration, let's say we assume that f is a continuous function defined on an interval. So we have an interval, a closed interval. And or you can either define your function as defined on an open interval. And let us assume the area between the graph of y equals to f of x and the x-axis is positive if the graph is above the x-axis, and negative if it's under the x-axis. So the reason why we define that way is because integral is not actually a sum of areas of graph, because we are going to add the values of function depending on the lengths where the function is defined. So when the value of function f is negative, we are going to add the negative values, and when it's positive, we're going to add a positive value. So when the graph of function is above the x-axis, that means function has a positive value, so we assume that area is positive. And when the value of function is negative, then the graph of a function is under the x-axis, so we're going to define the area is negative. So the integration of f of x from a to b is the sum of areas. So that area has a sign, positive or negative sign, between the graph of y equals to f of x and the x-axis. So here's the picture that you can see from the PDF file that I uploaded in the LMS site. So when you have this kind of picture, then this area is positive and this area is negative. So you add these two areas to define the integration of the function. So rigorous definition is the following. So when you define a integration, you're going to sum the approximate areas or areas of rectangles. So these are the areas of rectangle. Area of rectangle, and then you sum those areas and then send this limit to infinity. So I will explain shortly what this is about. So if the limit, so this is the limit of summation, exists, then for every choice of xi star lies between these subintervals, then we say f is integrable on this interval. So recall that we defined the function is differentiable at some point if there is a limit, if the limit exists, of the ratio of the limit exists. However, same thing for the integration. You're not simply define integral right away, before you define the integral value of function on some interval, you have to check whether this function is integrable or not. So when function is integrable, you're now able to define the integral of this function as the value of this limit. So this is the value of integral. Okay. So let me explain what this is. So let's say we have a positive function. Same thing for negative function. So let's say we have a function whose graph looks like this. Okay. If you cannot see clearly what I'm writing here, please let me know so that I can make a larger picture. So this is the graph of y equals to f of x. In order to find the actual area of a graph, you have to approximate your area by sum of areas of rectangles. So before you make a rectangle, you have to subdivide your interval of domain. So a is the first value of your interval, and b is the last value, xn. So yeah. So I'm going to subdivide total interval a to b as large n intervals. Okay. So I start from x0 and end at xn, so that there is a n subintervals. So n subintervals. And for each interval, I'm going to set a rectangle here. Now, this rectangle has the width. Width equals to delta xi, where delta xi is xi plus 1 minus xi. Okay. And what about the height? You have to set your height as somewhere between the minimum to maximum value of the function in this subinterval. You can set your height of the rectangle to the left height of the function, graph of a function, or right height of the function. However, you can either choose any value in between the value of function lying over these subintervals. So let's say I pick any point, I pick a random point here in between xi to xi plus 1 as xi star. So xi star is arbitrarily value in x-axis in between xi to xi plus 1. It can be either left-hand value or right-hand value. So if I pick this point, then my height will be here, fxi star. So the area of a rectangle whose width is delta xi and height is fxi star is now becomes fxi star times xi delta xi, right? And then we do this for each interval so that I get approximate area under this graph. So this area could be slightly bigger than the area under the graph or less than the area of a graph. However, what happens when I increase the number of its subinterval, large n, so when n goes to infinity, the summation from 1 to n of these areas, area of rectangles, delta xi, goes to the area under the graph. And this is the integral between integral of function from a to b. Okay. So this is the idea of defining the integration, and generally it's hard to check whether this summation has the finite limit or not. If you have a nice function such as polynomial or exponential or sine functions, you can easily check by standard method of convergence of summations, convergence of series. But in general, if you have a random functions which has lots of discontinuity and weird behavior, it's not easy to check whether the limit of this summation exists. So checking whether the function is integrable or not is not an easy problem, but we remarked that most of functions that we are going to talk about, like polynomial, exponential, or logarithm, or fraction of these functions are integrable on the domain where the function is not diverge. So as long as function does the value of function does not diverge on the interval, we can safely use the fact diverge. Sorry, so diverge. So as long as the function does not diverge on some interval at the endpoints, then we can safely use the fact that these functions are integrable. So the main point is to find the integral, not integral of the function given on the given interval, not whether not the checking whether this function is integrable or not. Okay. 네, 구분구적법이랑 똑같습니다. So there is in the lecture note. So in the lecture note, there is several ways to compute or approximate your integral using left limit, or left Riemann sum, or right Riemann sum, or triangulation, or using the other method, a Simpson's method, such as. We're not going to talk about that right now because I think there's no meaning. There's no point remembering all the methods of integration, because in the recitation session we're going to talk about how to take an integration in MATLAB, and MATLAB have all the algorithm to find the integration, and it has a very nice, a very robust algorithm to find almost actual value of integration for every function. So instead of talking about all the method of taking approximate value of integration, we are going to learn how to use the MATLAB to find the value of integration. So let's see. And there are some properties of integral. First one is, suppose that we have a value a and b, which is a is less than b. So the integral of f of x from b to a, not a to b, is the negative of integration from a to b. So usually when you take an integration, you have to take your interval of your integration from lower value, smaller value to larger value. However, you can define the integration from larger value to smaller value that's purely because of the computational reason, and we simply define that to be negative of the original. The reason is the following. So we had definition of integration as a sum of the area of a rectangle, and the width of the rectangle is defined as delta xi. Now, when you define your integration from a to b, the width is defined to be the value obtained by subtracting the smaller value, I mean left value, from the right value. But when you integrate from b to a, you simply interchange the order of your sequence. So when you integrate from b to a, this xn, the n value, the n value of the sequence becomes the initial value of the sequence, x0, and the first value of the sequence becomes the end value of the sequence. So that means you're going to interchange the role of this left and right side of the left and right side value of the subinterval. So this delta xi becomes the negative of delta xi when you switch the a and b. So this is very semantic reason. There's no meaning. There's no geometric meaning why the negative sign appears when you interchange the left limit and right limit. Okay. All right. So definition 0.3 is this one, I think. So this one, I think. So it says the absolute value of backward integral is equal to the forward integral. So it only changes the sign. So it means when you take the end value and start value as equal a, then it obviously becomes 0, because value which is equal to itself when you take the negative sign is 0 itself. Okay, so there are other properties that you already know. So when you take the linear combination of two functions, f and g, with coefficient k and l. So for your information, let me write the former name of this summation. So this is called this type of summation is linear combination. Sorry, so this is n combination of fx and gx. Okay, so this type of summation is called a linear combination. The reason why we call it linear is that there is no power to the function f and g. So it's an order 1 polynomial, a degree 1 polynomial, and you can also take the linear combination of 3 and 4 functions, 4 different functions, and this equality always hold. So you can split your linear combination of integrand. So the function inside of integral is called the integrand. So this equation means that you can split your linear combinations of integrand as a linear combination of integrals of each functions. Okay, so second one, for each c inside of the open interval a to b, you can split your integral. So you can, you have to assume that the function is well defined between a to b, and you can just cut your area of the function in between at some point C, and then add these areas of a graph of function separately, and then add it together, and that becomes the integral of entire domain. And when you have two functions, one is strictly less than or equal to the function, the other function on entire domain, the domain of interval, then the integration is also less than the integration of the other. So this is obvious. So another remark. So when you have a function which is not continuous at some point, you cannot take a differentiation at that point, because you have to have a value of function at a value when you're going to take a differentiation. But when you take an integration, you may have some finite point where function is not defined. So there's two types of functions where the function is not defined at some point. So let me give an example. So when a function is not continuous at point C, a function simply may not have a value at that point. A function may not have point, like it's just disconnected at the point C. Okay. So in this case, f of x has no value assigned at C, but if you looking carefully about this kind of functions, if you assign a specific value at C, so as the limit of the function when x approaches to C, this function becomes a continuous function at C. So this limit exists, and suppose that we assign the limit as L. So if you define your function, extend your function f to f tilde, and define f of x when x is not C but L when x is C, then this becomes continuous. This is one example when function is not continuous at some point, simply not defined, but you can make it as a continuous function with assigning suitable value at that point. Another situation is when the function diverges. So at C, function may have vertical asymptotic line, like this one. So in this case, you cannot assign a finite value at point C on the function so that this function becomes continuous. It's simply impossible. So this case, when x approaches to C, the value of function diverges. So there are two types of situations when you have a discontinuous situation. The first one, we're talking about the first situation. So it's not continuous, but it's not diverge. So in this case, when you try to define an integration from A to B, even though we don't have value assigned at the middle value C, you can simply separate the interval from A to B into two pieces, One is from A to C and the other from C to B, and then take the integration on each interval and add those together. So entire integration from A to B is simply defined as A to C to B summation. Okay. So in this example, we are assuming that C is the only discontinuous point of this function. So when you have a finitely many points, which is not continuous, then you can separate your integral into finitely many sums. So everything's okay. Let's look at the mean value theorem for integral. We have a function which is okay. So please ask question. Let me switch back to the blackboard. Okay, so I think when you when you program, if you define a function in a program, you cannot use the same symbol here. So I intentionally used the other symbol, which is f tilde. So f tilde is different function from f. So f has the domain not entirely from A to B. So the domain of the original function f does not contain the point C because C is not defined. So domain of f of x is A to C union C to B. However, I define f tilde as the function defined even at C. So when x is not equals to C, I define the value of this new function as same value of f of x, and when x is equals to C, another value, which is the limit. So in this case, the domain is A to B. So f and f tilde is different function because they have different domain. Does it make sense? Okay. Yeah, good question. Good question. So it's good to have a very rigorous argument. It's always when you define some mathematical terminology, we have to be rigorous. All right. Okay, so we have mean value theorem for integral. I have to draw it again. So let me just draw in this PDF file. So we have a function defined from A to B, and there is a graph of function in A to B. And when you take an integration from A to B, so that's the right hand side, and on the left hand side, it simply says there is a value in between A and B, says zeta here, so that if you take the value of function and take that as a height and height of the rectangle, and take, I'm sorry, so it has to be B minus A. it's a typo. B minus A as the width of this rectangle, then the area under this graph is equal to the area of this rectangle. So it makes sense, still makes sense, because suppose that the graph of function is the section of a surface of a water in a bottle. Okay, so you have a fluctuation of your surface of the water, and you're looking at the section of this surface, or side view of the surface, and at some point this surface becomes flat when there's no fluctuation. Okay, and at some point it should look like a rectangle, and the area of the section has to be the same as the area of the original, or area of the surface at the fluctuation. So there should be at some point the level or the height of the rectangle which has the equal area as the area of the graph. So intuitively, it should be this true. And I'm not going to give a rigorous proof. There's no meaning of giving a rigorous proof here. So in the example, it's a very simple example. If you're using the mean value theorem for integral, you can simply assume which one is minimum, which one is maximum of this integration without actually calculating the value of the integral. So when you take the square root of x squared plus 1, you know that this cannot be done using standard method of integration. Maybe you can do this for substituting the trigonometric function, but it's not simple here. But you can guess how much this value should be. So when you have, let me change this to blackboard. So when you have y equals to square root x squared plus 1, and we're taking the domain from 1 to 3. So at 1 becomes square root of 2, at 3 becomes square root of 10. So it looks like this one, right? Yeah. Bigger than the straight line. So we're going to take the area between 1 to 3 under the graph of function, but it's simply bigger than the area when I take the height as the height at x equals to 1. So this one has height 2 times, so this one is f of x, so f of 1, which is 2 times square root of 2. And also the area under the graph is less than the rectangle where I take the height at x equals to 3. So the height, the area under this rectangle is 2 times. So 2 comes from 3 minus 1. So this is the width, and f3, which is 2 square root of 10. So this is simply due to the mean value theorem of integration, because there's some point between 1 and 3, says zeta, such that if I take the height at zeta, let's say f zeta, then the area under this graph is equal to the area of the rectangle, right? But let me write it this way. So if I take the integration, actual integration, then that should be 2 times the width, 3 minus 1, times f zeta. And if I want the minimum and maximum value of this integration, I simply can take the minimum and maximum value of function, because this integration is simply 2 times the value of function. So even though we don't know what value of zeta should be, zeta is lying between 0 and 3, and when zeta runs from 1 to 3, the value of function has a minimum which is square root of 2 and maximum square root of 10. So that's where I get 2 square root of 2 and 2 square root of 10 as the minimum and maximum value of the integration. So you can actually do better if you use the mean value theorem, not mean value theorem of integration, right? How you can do that is looking at the graph of this function. You see, if you connect these 2 points, the end point and start points, there is a slope, right? So slope is somewhere 3 minus 1 and square root of 10 minus square root of 2. So 1 over 2 square root of 10 square root of 2, right? And what's next? If you use mean value theorem, there is some point, not the zeta, some other point, say zeta prime, such that at the zeta prime, the tangent line has the slope equals to the average slope between 1 and 3. So there's a point where the tangent line has the same slope as 1 over 2 square root of 10 minus square root of 2. So in that case, so we have these what's this shape called? Parallelogram, right? Parallelogram. And okay, so I think you need a little bit more calculation. So the smallest value that this area can have is the area of parallelogram, where you take the slope of this one and then take this side of parallelogram as the bottom of this graph. Okay, so if you take this side of parallelogram slightly above this line, and then until it reaches to the point where it tangentially meets the graph of function, then the area of this parallelogram is the maximum of the integral of the graph, integral of the function. So you can do a little bit better if you're using a parallelogram instead of rectangle. The actual value should be in order to find the actual value of minimum and maximum, you have to compute a little bit more. But I'm telling you that there is other way to approximate the minimum and maximum. Okay. So this is also well-known theorem, fundamental theorem of calculus. There are, this is a side note, there are many fundamental theorems in mathematics. So one is the fundamental theorem of calculus. There is a fundamental theorem of algebra, some fundamental theorem of algebra that every polynomial has a complex root. And what else? There's some other fundamental theorems. So this is I think the first fundamental theorem that mathematicians put the name fundamental. So the condition is that f is bounded. So which means that f does not diverge at the interval from a to b. So we have a closed interval. So it means that at the endpoints a and b, function still does not diverge. It has finite value. So then we define a large f as the integration from a to x of function. So x is now variable. So the endpoint, depending on which point we choose for the endpoints, the value of integration changes, and that value is defined as the value of new function large f. Then we have three properties. One is f is continuous, and f prime is the integrand small f, and that's the sometimes called the fundamental theorem of calculus. And for every point in between a and b, if you take the integration from c to d, it doesn't matter whether c is less than d or bigger than d. So as long as you have an order from c to d, then the value of integration is same as the subtraction of fd and fc. And also, you have to use the definition of integration to define, to prove these three properties, and also the definition of continuity and so on. I'm not going to define or prove this fundamental theorem of calculus. You have to understand what this means. So not just memorizing that the fact that if you take the integration and derivative, it becomes the same function. Simply understand what this means. So you have to know that this function is totally different function from the original function ft. So what it does is that you're taking an area, right? You're taking an area of a function from some endpoints to another endpoint, right? And let's look at the second one. So first and third actually follows from the easy properties of functions. So I'm going to skip this, and maybe I will put it as a homework. But let's look at the second one. So what it tells you about is the rate of change of increase or decrease of the area when I increase the right hand side of the x is same as the value of integration, right? If it makes sense intuitively, I think it's very okay. There's no problem. If it doesn't make sense intuitively, try to follow the definition of integration. So maybe I should put it in the blackboard again. So we are going to prove that f prime a is equals to fa. So although I omitted a in the property in the slide, there is a running from the interval, not a, sorry. So let's say t running from a to b. Okay. So how do you show this? So when you show whether a differential is some value, you have to follow the definition of differential. So differential is when h goes to t, h minus t to large f h minus large ft. So that's the differential at t. So in other words, you can choose your h to be goes to 0, and this becomes h plus t instead of h. Well, let's put it this way. So and then simply replace the numerator as the definition of large f. That's a to h of small f x dx minus a to t of small f dx, right? And well, this one is the integral, area from a to h, and this is area from a to t. So when you subtract these two areas, you simply are taking area between t to h, right? So this is t to h integral of fx dx divided by h minus t. Okay. Now, let's use the definition of integration here. So, h is approaching to t. So, when you take the approximate value of this integration, you can simply take the one subinterval between t and h. So although when you take the integration, you have to take a large number of subintervals, like large n subintervals, and large n, the number of subinterval goes to infinity. However, we are now taking the n value of the integral to be almost equal to the start value of the integral. So there's no need to take an infinite number of subintervals because it's a bit redundant here. So what happens here is simply we're approximately you can approximate your integral in the numerator as f t star times h minus t, right? Now, you can take any value of t star here, but you can also use the mean value theorem for integral. Then you don't have to take the approximate value of integral because mean value theorem for integration tells you that there is a point t star which makes this value, the height times the width, equals to the actual area under the graph. So then this integration, this fraction is not the approximate value of this this fraction is actually the same value of the fraction. So then what happens? We have same factor here. So we are taking a limit of ft star when h goes to t. So now t star lies between h and t, right? When h goes to t, t star must goes to t. So that becomes ft. So what we show here is that f prime t is equals to ft if you follow the definition of integration. So this is a rigorous way to prove the fundamental theorem of calculus. If your intuition doesn't make sense to you, you can just follow this rigorous proof of fundamental theorem of calculus. Okay. If you have any questions, please ask. Okay, so the next one, instead of taking a value of integration, n values of integration, we can take the function on the limits of this integration. Let's say we have integration of ft, so now t is just intermediate variable, so it doesn't have meaning here. Simply assume that t is ranging from ux and vx, and now x is a variable, so we're going to take a derivative in terms of x of this function. So entire integration is the value of function depending on the variable x, and now we're going to take a differential in terms of x. Then we have these functions. Okay, so you can also prove this simply by considering this differentiation or taking this integration as the composite of function large f vx minus large f ux. Okay, because you can rewrite your integration as suitable integration to Vx ft dt minus a to ux ft dt. Okay. So, and then make this into the composition, and then use the standard rule of taking derivative of composite functions and the fundamental theorem of calculus. So this is an example that you can take an integration. So this is obvious to you, I think. So let me talk about indefinite integral. Maybe we cannot go through entire sections here. So far, until the Leibniz rule, we only talked about the function, integration of function, where the function has a finite value on the interval, on the entire interval, a closed interval. Before when they said when I said the discontinuous type of the function, the second type of discontinuity is about the diverging, the point where the function diverges, right? So there is a way, there is a method of taking an integration of the function where the function diverges at some point. So I'm sorry, this is the indefinite integral. I'm confused with the improper integral. So before we talk about the improper integral, let's talk about the indefinite integral. So the definition, we have a continuous function, and we simply call a large f antiderivative function of function f if the derivative is the original function. So indefinite integral is also different from the definite integral. Definite integral is the value, okay? So definite integral is the value of area of a function or the limit of the sum, Riemann sum. But indefinite integral means that it's the family of function. We're taking entire family, infinite family of function, which can be an antiderivative of the original function. So usually we put C to represent this is the family, because C ranges for entire real line. So we simply write the family of such functions as this symbol. Okay, so symbol without the limits here. Okay, and the reason why we just taking an indefinite integral is if you know the family of function, then since each member of the family only differ by a constant, so by looking at the fundamental form of this family, you can simply take a definite integral by plug in the value inside of this fundamental form of indefinite integral, and using the fundamental theorem of calculus, you can find the definite integral value. So there's a well-known formula for indefinite integral. I think you all know you already understand why it is true. Okay, so also there's a method of taking integration. I have to ask you whether you learned this in high school or not, because the curriculum always changes. So I heard that in 2015 curriculum, high school curriculum, they don't even learn how to take an integration or how to take a derivative of fractions of functions. 이거 배웠어요? 부분적분이랑 그 치환적분 배워요? Okay, so I don't have to go through all this one. Thank you. So let's take the few computations here. How about the first one? So let me switch back to the Blackboard. first one, square root of x dx. So you have to, when this power is not square root of x instead of, if it's u instead of square root of x, we could take an integration simply, simply using the fact that the integration of e to the x is e to the x. So we are going to take a substitution square root of x into another symbol u. So we're going to take u, e to the u, and then now dx makes a problem. So you have to substitute the dx in some form of du. So let's take the differentiation of u in terms of x, then du equals to 2 square root of x dx, and then now everything is in terms of u, so you have to also change this in terms of u, so this is 2u dx. Okay, so in other words, dx is equals to 2u du, and then substitute back to the integration, you have 2u du. Okay, and then let me rewrite this into 2u squared e to the u du. Now, this is not a simple integration. There is a, I think there's a scheme to take integration by parts simply, but I will follow the standard method. So when you take a differentiation of the polynomial, it basically becomes 0, right? It becomes constant and then 0. When you take an integration of exponential function, it still stays in its exponential form. So we're going to take integration and differentiation, diff on each side. So diff here and integration here. So basically we are going to assume that this one, did I use, let me just, yeah, okay. So this one as f of x, and this one as so f of u, and this one as g prime of u. So the formula says that the integration is nothing but fu gu minus of f prime u gu du, right? So fu is equal to 2u squared, and gu is simply eu, and minus of, now we're taking the first derivative of the polynomial, we have 4u, and then gu is eu du. And we do the same thing for this integral. So now we have a degree 1 polynomial here, so we're going to take a differentiation here and integration here. So also change this to fu, and this one as g prime u. Okay, and then we get u, let me stay here. Okay, so 2u squared times eu minus, so put a big parenthesis here, 4u times eu minus, now take the derivative of f prime, so we get 4 times gu, which is eu. Okay, let me write above. So we are almost done. We have 2u squared eu, and then minus 4u eu, and then minus, so it's a plus, and then integration is simply eu, so we get 4eu, then plus c. Okay, so now this is not over, because in the beginning we have an integration in terms of x, so we have to write the answer in terms of x. So the final answer is 2. Now u is square root of x, so u squared is x, and e to the square root of x minus 4 square root of x, and e to the square root of x plus 4 e to the square root of x plus c. So this is the answer. Okay. So it's important that you have to be able to compute this by hand, but also it's important to how to find this answer using MATLAB. So we're going to practice how to do this in MATLAB. Okay, so should I do the other ones? I think the other ones are also standard example. So number two is also standard example of integration by parts, and number 3 also the standard trick of taking integration by parts, right? Okay, so here's another remark. So as I said, there's several fundamental theorem of mathematics. So the other fundamental theorem, called the fundamental theorem of algebra, tells us that every polynomial has a root, which means that you can always split any polynomial into first order linear terms. Okay, so let me write again here. So let me read the slide first and then write on the blackboard. So this implies that every polynomial p of degree n has exactly n roots. So suppose that we have px has a k real root and 2l complex root. Why we have a even number of complex root? We always have a conjugate pair of a root if the root is complex. So if complex roots always comes in conjugate pairs. So if b1 plus c1 square root of minus 1 is a root of a polynomial, then you always have another conjugate root b1 minus of c1 square root of minus 1. So in that case, you have following decomposition. So a1 to ak are real roots, and these one are the degree of the root. So 중근이라고 하죠. 이게 이제 m1이 1보다 크면. So and then the other roots, complex roots, are decomposed into the quadratic form of the polynomial. You can further split this quadratic form into the linear terms, but then you have to use the complex numbers instead of real numbers. So this a1, b1, c1, and ai, bi, ci are all real numbers. So this is the furthest way you can decompose your polynomial of real coefficients. You cannot decompose further using the real numbers, real coefficients. So this is the important part. So when you understand this remark, you can always decompose your fractions into these forms. Okay. It seems very complicated. So let me split this form into several parts. So first part is the numerator. It's the part when you take a differentiation, the division of qx by px. So if the degree of qx is bigger than or equal to px, these ax terms always survive. 이건 몫이라고 하죠. 이게 이제 폴리노미라고 했을 때 qx랑 px가 둘 다 폴리노미얼이라고 했을 때 몫이 하나 나오는 거예요. So this always appears when the degree of Q is bigger than or equal to degree of P. Okay. And then this term follows from a term where XA1 to the M1 to the and then some denominator whose degree is less than strictly less than M1. Okay, and same thing for these terms. So you have fractions of polynomials in the numerator. So you're going to split all the numerators, and then each numerator, such as x minus a1, has the denominator, which is the polynomial whose degree is less than m1. And then you're going to further split this numerator or denominator into powers of x minus a1 from power of 1 to the power of m1, and same thing for other terms, and same thing for other terms in the complex roots. So we have at first you have a power denominator as a power of n1, but you're going to split into power of 1 to the n1, and same thing for here. So I think it's better to look at the example here. So we have let's look at the first one and second, both of examples here. So before we take the integration, just take the integrand, x squared minus 2x minus 3, and then 2x cubed minus 4x squared minus x minus 3. Okay. Now, you see the degree of the numerator is 3 and denominator is 2. So we have ax term. How to find the ax term? You simply take 2x3 minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3. You take the you match the highest order, highest degree terms here. So highest degree term in the numerator is 2x squared, in denominator x squared. So in order to match these two terms, you have to multiply 2x. So then you have 2x cubed minus 4x squared minus 6x. When you subtract these, you have cancel out these two terms, and we have 5x minus 3. Now, this one is degree 1 and this is degree 2. You cannot divide further. So these 2x survive, 2x, and then the rest terms is x squared minus 2x minus 3 and 5x minus 3. Now, you can simply take the fractions here. So we have x minus 3, x plus 1, and 5x minus 3. So you can divide your denominator. Okay. X minus 3 to the a, and then so let's put big parentheses here. So x plus 1 b. So what's on this side of numerator for each denominator here is that a and b, these terms should be a degree less than 1 terms. Okay, so this one has degree less than the numerator. The 5x minus 3 is degree 1. So therefore, if you split the numerator here, the numerator for each fraction has to have degree less than the degree of denominator. Sorry. So this a and b is degree 0 terms. So degree 0 means that it's constant. Okay, so a, b are simply constant. So you have to find what a and b are so that this makes these fractions here. So let's say a times x minus 3 plus b times x minus, so x plus 1, x plus 1, x minus 3 is equals to 5x minus 3. So if you compare the coefficients of x, a plus b becomes 5, and a minus b, 3b, equals to minus 3. So it's a simple calculation to find a and b. Then you have a split of your fractions. So when you take an indefinite integral of these functions, x squared minus 2x minus 3 and 2x cubed minus 4x squared minus x minus 3 dx, you can use this form. We assume that we found a and b. So it's same thing as taking integration of x minus 3a and x plus 1b. Okay? And then simply take the integration. We have x squared and minus a times log, the natural log, and x minus 3, absolute value. And then minus b log x plus 1 plus some constant. Okay? Now, this one is simple. Let's look at the second one. So, if any questions, please ask. I will wait about 10 seconds. Okay, so let's look at, we have questions. Oh, yes, plus. So everything is plus. Yeah, thank you. 또, 자, 이해가 안 되신다는 분. a minus 3b equals to minus 3. 얘는 틀린 건 없죠? 자, 이건 한국말로 할게요. 자, 지금 통분한 거예요. 분모를 통분했어요. 요거랑 맞추기 위해서. 그러면은 a에다가 x 플러스 1 곱하고 b에다가 x 마이너스 3 곱하고, 그러면 이제 분자가 이제 요런 형태가 될 거 아니에요? 근데 요게 원래 이제 프랙션의 분자랑 똑같아야 되잖아요. 그러면은 요거랑 같아야 되는데 이게 이제 똑같은 항등식이 돼야 된다고요. a랑 b, 그러니까 x의 개수인 a 플러스 b를 구했을 때 5가 돼야 되고, 그 다음에 상수항 a 마이너스 3b가 마이너스 3가 돼야 되죠. 그리고 이제 a, b는 연립 방정식으로 풀면 되죠. 네. 자, let's look at the second example and then finish the lecture. So we have x to the fourth plus 1 over x to the fourth plus 1. And then take the integration here. So every polynomial has a complex root, okay? So this one has also complex root. So how do we find a complex root? This is a very tricky problem, but I'm simply showing that through this example you can always split your polynomial into either linear terms, powers of linear terms, or powers of quadratic terms. So think about your x to the fourth power plus 1 as x squared plus 1, x squared plus 1. And then if you have these two terms, and I'm going to add something and minus something, okay? So when I do this, I simply get x squared plus 1 square, right, minus of this red box square, right? So what do I have on the first part is x squared plus 1, which I want in the beginning, and some other terms which becomes 2x squared, right? So I don't want these terms. This is auxiliary. So I'm going to subtract these 2x squared terms by square of red box. So red box should be 2x squared, but red box should be square root of 2x. So square root of 2x squared, right? So basically if I had 2x squared, square root of 2x, square root of 2x, square root of 2x, I have x fourth to the x fourth plus 1. And then these are the denominator, not numerator. So we are going to use here x squared plus square root of x 2x plus 1, and then x squared minus square root of x plus 1, and then we're going to split the denominator here. Now, as I said, this one is a polynomial. It's a constant polynomial, and degree 0. And this one has degree 4, right? So there's no ax term. However, we have term survives here, and these terms has to be the degree 1 less than the degree of denominator. So we have to expect that this should be ax plus b, and this is cx plus d. So the important part is that these are 1 less degree than the degree of denominator. Okay, so that's the order degree 1 polynomial. So now the question is to find the a, b, c, d by taking the denominator all together and then make it into 1. Okay, I leave it to the exercise, leave it as on homework to find this a and a to d. Suppose we found that, and how do you find? How do you compute further? So, and then we are going to take x squared plus square root of 2x plus 1. Okay, and then now suppose that we are going to take an integration of the first part. Okay, so when you substitute the entire numerator into u, then this du becomes 2x plus square root of 2. So I'm going to use these terms, 2x plus square root of 2 and a over 2. Okay, so then we have ax term survive here. And the rest of the term, so in the dx, so we have dx here. Yeah, so this one is dx. And the rest of the term is becomes x squared, square root of x plus 1 to, first of all, b is here, okay? And then I have to get rid of this auxiliary constant term. So we have minus a over square root of 2 dx. So that's the integration from the first part of the summation. Okay, so first part of summation is same as sum of these two integration. Okay, and you can do the same thing for the second part. So I'm not going to write all down here. And let me erase right here. So how do you take the integration for this one? You can simply substitute the entire denominator. So you get log of x squared plus square root of x root of 2x plus 1. So that's the integration. Okay. How about this one? So you have to use the trigonometric function. So you have x plus, and you have to take a perfect form of the quadratic equation. So 1 over square root of 2 over 2 square plus, now this one becomes 1 minus 1 over 2, so it's 1 over 2, right? So 1 over 2. And then some constant, so it doesn't matter which constant it is, but b minus a over square root of 2, so dx. And then you use the trigonometric function. So this part is now substitute as, so we have tangent theta equals to, tangent theta plus 1 equals to secant theta, right? So cosine sine, yeah. So I'm going to substitute entire x plus square root of 2 divide by 2 as tangent theta. And so this one is okay. So this one is fine. Only I'm taking this part. So the ln part. So ln plus, and now this part becomes integration of okay, so I have to take the square 1 over 2 also change it to 1. So I'm going to take multiplying 2 on the both side here, so 2 here. So then this part becomes 1, and now 2 times of square root 2 times of x plus square root of 2 over 2 is tangent x. Okay. So then this part becomes tangent square theta plus 1, and there's some constant, whatever constant it is. And what is dx? So if I substitute this way, I get square root of dx, square root of dx as, if I take a derivative of tangent is secant square, right? Secant square, right? Yeah. So dx becomes square root of 2 secant square d theta, right? So here's the parenthesis. I'm sorry that this becomes messy, but let me erase this part, okay, so that I can write at least one answer of the part in the integration. So the final answer of the first part, so you can do the same thing for the second part, is the ln of x squared plus square root 2x plus 1. And then now I'm going to take a differentiation here, but you see the tangent square theta plus 1 is secant square. So this cancels with this one. So this cancels out. Everything cancels out. So only square root of 2 and this constant survive. So square root of 2 and this one, 2b minus 2 square root of 2a survive. And we're taking derivative in terms of theta instead, not x, okay? So now the answer is ln plus ln this one plus these constant. I'm not going to make it simpler. So this one is 2b minus 2 square root of a, and then what we have here is just simply theta, right? When you take an integration of constant, you get just theta here. But theta is defined in this formula. Tangent theta is the function of x. So we're going to take an inverse of tangent, arctangent. So arctangent of what? These thing. So we have square root of 2x plus 2 square root of 2. Okay? And plus c, because this is an indefinite integral. So this part is the integral of the first integration here. So you can do the same thing for the second part. So it looks simpler, but answer is not simple. Make sense? If you have any question, please ask right now. No questions? 다 이해되셨어요? 네. Okay, let's move on to the MATLAB today. 네. Okay. Okay, let's take a new one. So this is week 3. New script. Okay. So this week we're going to talk about the symbolic toolbox. So I think this is a very useful toolbox that you can use in mathematics, even when you're taking other courses like multivariable calculus or linear algebra. or complex analysis, you can use this symbolic toolbox in many places. So basically, this toolbox can do all the all the computations that you can do by your hand, because it has all the algorithm to find the computation, if you can all the computation that can be done by hand. So for example, I'm going to take a differentiation, and in order to take a differentiation, you have to assign a variable as a symbolic variable. So this is called as defining a variable x as symbolic variable. Okay, and then let's define a function. So x squared, defining as this is actually a formula, symbolic formula. So even though you didn't define variable f as a symbolic variable, when you do this, then f is automatically becomes symbolic formula. So after you do this, when you take f, differentiation of f in terms of x, by typing the command diff f comma x, it means that you're taking a differentiation of this formula f in terms of variable x. So let's run this. Okay, so answer is now 2x, right? Yeah, so it gives the formula here. How about the integration? Int fx. So you get the integration right here. Okay. What else? Let's okay, so we had a long computation, so let's find out what happens when we do the integration that we did in by hand. Integration 1 over x4 plus 1. So now you don't have to put the dot when you define symbolic formula. So dot is only when you take a array of numbers, and then try to compute each value of array. But this one, the symbolic variable is not the value. It's not a number. It's not a number of array. It's just symbolic object that MATLAB uses in their algorithm. So let's try to take integration of 1 over x4 plus 1. So I defined my x as a symbolic variable, so I didn't clear this x yet. So still this x is symbolic variable, so I can use this formula as a symbolic formula, right? So and then integrate this one as in terms of x. Okay. So you see there are long computations. So these are the answer. So it's not simple, quite long. Maybe sometimes you can use simplify command to make it simpler. This one can be simplified further. So this one is simplest form. Sometimes you can put simplify command so that it makes it simpler. Okay, so differentiation, integration, and what else? Okay, so you can substitute the substitute some formula. Let's say we have function already defined as x squared. So I'm going to define another variable, sims a as a symbolic variable, and then subs fx into a plus 1. Okay. So result is that instead of x squared, you have a plus 1 squared. So what does it mean? So I substitute x as a plus 1. Okay. So f inside the formula f, there is a symbol f, symbol x, and x is substitute as a plus 1 formula. Okay, so that's the result, a plus 1 squared instead of x squared. So now it becomes the function of a. However, when you define your variable g and try to define, you can define variable a as the input variable of g. And then you can also define your function g as a result of substitution as a function of x and a altogether. So when you define that way, even though there is no variable x appeared in this formula, MATLAB assumes that this g is two variable functions, so x is simply not defined in the formula, but there is a variable x hidden, not hidden, it's just not appeared yet in the formula. Okay, so simply it's just the constant in terms of x. So there's a big difference when you assign the input variable for symbolic functions as two variable functions or single variable functions, because now if I define this way, I try to define compute the differentiation of g in terms of x. So result of this differentiation, when I take a differentiation of g in terms of x, is 0. Okay, x and a are not related, they are not a function to each other. So okay, so there's no variable x appeared in the formula of g, right here, no x. So when I take a differentiation of x, a is considered as a constant. So this is a concept of partial derivative. So there's no special formula, there's no special command to take a partial derivative instead of derivative. So just simply diff command do both derivative and partial derivative. So when I take a differentiation of g in terms of x, I'm taking a partial derivative of these two variable functions, and the result is 0. But when I take a derivative of a, then the result is 2a plus 2, which is the same as the derivative of a plus 1 squared. Okay. When I defined my function g as a single variable function, this still makes sense because I'm taking a single variable function g in terms of a, taking differentiation in terms of a. But when I take a differentiation in terms of x, okay, so this also has no error, but sometimes you could have an error because now this is not defined in terms of x, but in this case MATLAB considers this g as a symbolic formula in terms of x and a. Okay, so there's no problem here, but you have to take carefully when you define your function, because sometimes it makes problem when you take a differentiation of one variable. Depending on whether the function is defined as multivariable function or single variable function, result is very different. So since we're not going to talk about the partial derivative or multivariable functions, but when you solve the differential equation, the concept of partial derivative appears shortly as soon as we talk about the solving differential equation on the next week. There is a concept of partial derivative, so you have to understand these are different integrations. Okay, so another one. This is a symbolic method of taking derivative and differentiation. Let me briefly mention about how to take a numerical integration. So let's say we have x squared, and I'm going to take an integral of this function from 0 to 1. Okay. So you see the answer is now given as a number. Okay. It's given as 0.333. Basically, if you integrate x squared from 0 to 1, you get 1 over 3, right? This integral command gives an analytic solution, which means the approximate number of this integral value. Okay. However, when you take an integration symbolically, I'm sorry. So I defined f. Okay, so let me define another function. So fs as the symbolic function here, and integrate fs x from 0 to 1. Now it has a actual value 1 over 3. So the first one is approximate value of integration, and this one is the exact value of integration. So x is already defined as symbolic variable, so sims x here, and small f here is defined as numerical, as anonymous function, so numerical function. But now this one is symbolic function. Okay, so the command here, the int is the integration in the symbolic toolbox. It computes the exact value of integration of formula fs, which is x squared, in terms of x, from the initial value 0 to the end value 1. Okay, so the answer is same, but in the first one you can only get the approximate value, but the second one you can get exact value. So there's a pros and cons. So the integral, the approximate value is useful when the integration cannot be done by hand. You can only guess the exact value by approximate the integration. Then you have to use the integrals command. But if your integration can be done by hand, and somehow you don't know how to do by yourself, then you can check your integration, the answer of this integration, by using the int command and symbolic toolbox, and then this gives you the exact value, exact answer of this integration. So basically, if the int command gives a specific answer, then there is a way to compute this integration by hand. So somehow you have to be able to do this by yourself. But sometimes it's hard to memorize all the integration techniques. So sometimes you can just use this symbolic method to find the answer. Okay, so this is it for the integration. So next time on Thursday, we're going to talk about improper integral and some properties of integration and some other application of integration, like finding the area or finding volumes of a surface, volumes of this 3D object. So thank you for listening, and let me finish up by announcing the homework and quiz. So on Thursday, I'm going to give a homework. I'm going to upload that into the LMS site, LMS webpage. And also, I'm going to upload a deadline to the homework. And on the next week, we're going to have a quiz. We're going to have quiz on either Monday or Thursday. So I'm not going to announce which day I'm going to take a quiz. So it's be either in Monday or Thursday that we're going to take a quiz. So quiz is on right after the lecture on recitation session. It's about 30 minutes long, and I will give some extra time from 5 minutes to 10 minutes so that you can upload your solution in PDF form into the LMS site. So I'm going to demonstrate how to do that, in how to submit your quiz on Thursday. Okay, thank you. Yeah, so that is it. Have a nice lunch and see you on Thursday. Thank you.